Using first channel, the user equipment identifies the start of a slot, end of a slot, and the radio frame. Using second channel, the user identifies the slot number and the group number using the table, and the table is known to the user. And using the third channel, from among the 8 code in that particular group, or to identify the group, the user equipment correlates and finds the scrambling code of that node B.
Very good answer. Great job. Just a slight mistake. Like the first step, or the use of first channel, primary synchronization channel, enables the determination of the slot boundaries only, not the radio frame boundaries. So it comes to know where the slots start. Every radio frame has 15 slots. Okay, so it still doesn't know where the radio frames are starting. In the second stage, using the secondary synchronization channel, it can identify the radio frame boundary. Okay. So then the synchronization or time alignment is complete. In the second step, it also gets an idea, or it reduces the search space for the scrambling code from 512 to only 8. Okay, so in the second step, you have twofold achievements. We know that we have to also find out the scrambling code used in the downlink. It's called PSC. So that is partly done in the second step. You know that it would be one of these 8. In the third step, you correlate with your PSC, and that's a long correlation, but the search space is only 8, so it won't take long. It's manageable. Okay, so you keep trying. Well, you even in the first attempt, you may find out correlation peak, and so you converge to the PSC, or in second, third, or fourth attempt, you may be able to find out PSC. But that will be not too burdensome because it's only 8. Okay. Yep.
Then I have some few questions based on
Mhm.
one of them is, sir, is there any gap between two radio frame of 10 milliseconds?
No. You keep sending the chips one after another. 30,400 chips form one radio frame, but there's actually the chips are sent continuously one after another. They are all identical. From the UE end, it doesn't find any sort of boundaries. Okay, there is no difference between two consecutive transmissions of symbols or chips. Okay, and that's true for all 2G, 3G, 4G, 5G technologies. It always keeps sending the symbols one after another, either in downlink or uplink. You keep doing that. Okay, so unless you have this type of synchronization, you cannot identify the beginning or the end of packets, okay, or say whatever types of framing you use. Of course, in the time domain, you have some, always you have some segmentation or framing. Okay, this range of symbols form one form of frame. Okay. But from the receiving end, you have absolutely no difference between any two consecutive transmissions of symbols. Okay, so from there is no way you can find out. Okay, so just chips are 30,400 chips are sent in every 10 milliseconds. So in 1 second you have 3.84 mega chips. Okay.
And second question is, sir, these three channels, they are in different, they are transmitted in three different frequencies, right?
No, absolutely not. You have just one frequency for transmission in CDMA. If you have least 5 megahertz, okay, that 5 megahertz you have to use. Actually, I mean, it's always 5 megahertz bandwidth. If you have another 5 megahertz bandwidth, then you can just overlap that one, and that will also have another, I mean, this set of channels. Okay. So it all uses. The way you
So, sir,
So how do you then identify the channel? This is the question, right? So you have to assign an OVSF code. You have separate OVSF codes for PCH, PSCH, primary synchronous channel, for secondary synchronous channel, SSCH, and for CPH, I mean common pilot channel. You have all separate OVSF codes for them. And there are many other control channels. We are not discussing 3G, but you know, I mean that's also a vast area. So the different control channels all have different OVSF codes. Remember, okay, keep it in mind. I mean, this discussion. Actually, I wanted to say a few things. Now I remember. I told you before that the capacity of voice calls is close to 100 in 1.5 megahertz deployment for CDMA, right? Do you remember?
Yes, sir.
Okay. I also told you that the usual spreading factor for voice call is 128. 128. Okay. So when you have 120, if you go down to 128 spreading factor level in the OVSF tree, then of course you have 128 OVSF codes available, which you can assign. However, part of the OVSF tree will be occupied for control channels. So they all will not be available for data purposes. So once you leave them out, you have a number close to, at this level of 128, you have something close to 100 available. Okay. However, you can make it actually 100 or around 100, but there in CDMA it's also it's not a fixed number how many you can assign. Okay, from OVSF code tree you have some the control channels also are not exactly fixed. Okay, few control channels are sometimes they appear or disappear. Okay, so I don't I shouldn't say that it's a fixed number how many voice calls you can set up, but it is really very close to 100. We calculated using a number 97, so it is around that number usually. Okay, for a cell. Now it's also not fixed because of the noise level generated in the CDMA environment. In CDMA, it is very critical that you have proper power control, because we mentioned that when you have multiple languages in a party, then you can communicate with somebody as long as the number of speakers in other languages are not too high. That's not too high. If it is too high, then the languages are not understandable, but they feel like some noise, background noise. So the background noise will be too much, and so you cannot detect the speech of your counterpart. So you have to, the background noise you have to control. And how do you do that? Let other people use as much power or barely as much power as they need. Okay, so the better you can control. So everybody should be using barely as much. Well, that is true for all technologies. Okay, 2G, 4G. In all cases, interference or proper interference control, it is important. But in CDMA, it is more important. In CDMA, they don't look like direct interference. It is like, I mean, all frequencies are left open. Okay, if you call it interference, then, I mean, all are interferences. It is rather something like noise. Okay, in other technologies, when you have a frequency match, okay, everybody is using different frequencies. When there is a frequency match, so it is then called interference. But here it is treated differently. Everybody is using the same bandwidth, same frequency, the whole 5 megahertz, but it just sounds like some I mean noise, background noise. So you have to, I mean, when you use, if you use louder, if you use high power, then your partner will be able to listen you better. That will definitely happen, but it will hamper other users. Okay, like in a party when people are using different languages, if you increase your sound level, your partner will be able to hear you better. Okay, but other people in the party will be in trouble. So similarly, this is why in CDMA the power control is more delicate, and I mean it is done with even better care. The maximum frequency of power control, okay, how the power control is done from the base station for either downlink or uplink. Now, so for uplink, the base station sends some control or some commands, okay, as we'll see later. Send some commands that increase your power level or decrease your power level. This type of command, how frequently the base station can send, okay, at the maximum. What is the maximum frequency to send this type of command that, okay, increase or decrease your power level? Even in 4G, in LTE, the maximum frequency is 1000. Okay, I mean in every millisecond, it's possible that the base station sends a command at the maximum. Whereas in CDMA, it is 1500 times a second. Okay, like I mean, you have slots. Right? In the slots, you can send the command. It is just made, the frequency is made just too high to have a better control of power transmission. Okay. Okay, and sometimes you'll find a term rise over thermal. It always, the base station always also keeps checking how much power level currently there is in the cell above the thermal noise level. Okay, we know what thermal noise level is. The noise floor we discussed last time. There's the thermal, because of thermal noise, you have some noise flow in the environment. So it keeps checking how much the current, because of current uses, how much the background noise is, how much noise you have, okay, power you have above that thermal noise level. Depending on that, it is called rise over thermal, ROT. Depending on that, it decides how many voice calls you should assign or how much, okay. So, I mean, how the capacity in the cell depends on rise over thermal in the CDM system. Okay. Let me just write down this term rise over thermal. In CDMA, the actual capacity or the practical capacity depends largely depends on rise over thermal. Okay, in the chat box I have written down. Any other question? You are Ratul, right? Are you
Yes,
Ratul?
sir. Yes,
okay.
sir.
So do you have any other questions?
So right now I have no
You don't.
questions.
Okay. Okay. Very good. You've raised good questions. Let's go back to our presentation. We had a brief introduction of WebGen, and the subcarrier spacing is held fixed at 15 kilohertz. It's what we mentioned last time. Now, what can be the total bandwidth in 2G? It can be anything, okay, for a cell. In 3G, it has to be 5 megahertz. You can have multiple 5 megahertz overlapped on each other. And in the case of LTE, it's also possible that you have overlapping kind of thing. But normally you don't need to. You have different types of bandwidth allowed in the spec, total bandwidth allowed in the spec, and these are actually 6. So you know, they can take on these particular values: 1.4 megahertz, 3, 5, 10, 15, up to 20 megahertz. Okay. And it is also called scalable because you may be currently deploying 5 megahertz, but you have got more users or more customers, so you want to increase the capacity. So you purchase more frequencies from the government, and if that is the new bandwidth you have got, it's just next to your current spectrum. Okay, maybe you had previously say 1920 to 25, and another 5 megahertz you have got from 25 to 30. So they are adjacent. So in that case, you can just increase the total bandwidth from 5 to 10. In CDMA, you can't do that. You have to have another 5 megahertz deployment overlapped. Okay. But here you can just increase your total bandwidth, operating bandwidth. You can make it 10. Or you can increase it to 15, 20, as long as you have contiguous bandwidth available. So it is scalable. You can change. The number of subcarriers, well, allowing small guard band at the two sides. There are it's 15 kilohertz. So probably you can check, multiply, okay, that the total will be close to 10. Okay, it's like we have 1600 and 15 kilohertz. So now it is like 9 megahertz. So it is close to 10, and the residual part is used as guard. Okay. So anyway, that's how you have the total bandwidth allocation and the number of subcarriers. So they have fixed values. Now I was telling about the possibility of overlapping kind of thing. Okay, yeah, that is possible. That has been introduced in release 11. It is called carrier aggregation. So I'll just use the chat box to write down this term. Sorry. Carrier aggregation, in short CA, introduced in release 11. What it does, if you have already 20 megahertz, but you need more, then what you can do, you can have, say, another 20 megahertz. In the specification, the maximum bandwidth is 20. But you can have another 20 megahertz, which may be contiguous or not. But you can have also deployment, and you can have an aggregation of these two. Okay, I mean there will be overall operation over this whole range. Okay, 20 is say 20 plus 20, say 40, and then there can be another 20. Okay, this way on and on, you can have up to 520 megahertz bandwidth. So allowing the maximum with carrier aggregation. Someone can join the class, but okay, let me just respond to her. Okay, she could join already. Okay, so we're discussing carrier aggregation. So 20 megahertz deployment is the maximum normally, but multiple 20 megahertz deployment is possible. And this way, up to 5 deployments you can aggregate together. So the new maximum is 100 megahertz. Okay, with CA or carrier aggregation, the maximum bandwidth support is 100 megahertz, which is actually composed of 5 20 megahertz deployment. Okay, so they all together work. Okay, sorry. Okay, the last row we'll discuss later. We'll come back here after we discuss something else. There are some segmentations in both time and frequency domain. In time domain, you keep sending symbols one after another. We have symbols instead of bits because we already know from the last semester that we use different types of modulation lasers, QPSK and 16 QAM. Okay, for data, BPSK is not there, so there will be at least 2 bits in a symbol in LT. So the lowest one is QPSK, then you have 16 QAM, 64 QAM, 256 QAM, and 1024 QAM in the recent release, in release 15, 1024 QAM has been added. So these symbols are just transmitted one after another, as I said a while ago. There's normally no way to separate, to identify, okay, any boundaries. However, one symbol period is little larger than its neighbors, okay, as we'll see shortly. But that's not a major issue, okay. And there's a slight difference to have to fit in the size that we have in our second or millisecond I mean culture, okay, the tradition that we have, millisecond. So the time length we have, so the symbol length requirement is little different. So to fit in a particular symbol is little extended. Anyway, so in the time domain, we have some frames like in CDM, and the radio frame length is also called radio frame, like 3G, and its length is also held at 10 milliseconds to make it compatible with 3G. Okay. However, in 3G you had 15 slots, but here you first have some subframes. Okay. Down from radio frame you have subframes, and you have 10. So every subframe is 1 millisecond long, and then in one subframe you have 2 slots, each 1.5 millisecond long. So actually you have 20 slots in a radio frame, but subframe boundaries are more important. Now in a slot you have, I didn't show it here, sorry. Okay. In a slot, as you can see this way, this is the time axis, and this way, and I mean we have some blue bars. This is the frequency axis. We have 15 kilohertz subcarriers taking up some, bandwidth, 15 kilohertz bandwidth around each subcarrier. Now we're showing one slot here up to this point. Okay, this is one slot, and so you have symbols one after another. Now normally you have 7 symbols in one slot. There are actually 2 possibilities. You can have either 7 symbols in a slot or 6 symbols in a slot. Okay, so in 0.5 millisecond you have 7 symbols. Now you have an idea how long a symbol is, but I'll give you the exact symbol length the next day. Or let's go this way. I'll share some scanned pages from my book with the exact length, and you'll see that the first slot is little larger in a slot. Okay, and the rest 6 have equal length, but that is just to fit in the 0.5 millisecond length. Okay. So anyway, normally you have 7 symbols in a slot, and in some special case you have 6 symbols. Okay, I'll tell you later what that is special case is. But you keep sending. So in the next slot of the same subframe you have again 7 symbols. So in one subframe you have 14 symbols, and this way you keep sending on and on, okay, for the whole radio frame. Then the next radio frame will appear. Well, now in the frequency domain we also have a number of subcarriers, and that is fixed. We know that we have a fixed operating range. Say if we have 10 megahertz bandwidth of operation, then we have 600 subcarriers available. So we will have to transmit onto all the subcarriers together. Like you see, symbols are transmitted, say here, okay, at this symbol period. You transmit symbols on all the subcarriers together. Okay, you have synchronous modulation and transmission for all the subcarriers. Okay. Now you have some concept of blocking with, creating some group with every 12 subcarriers. And 12 subcarriers take up 180 kilohertz because of 15 kilohertz subcarrier spacing. Okay, so 180 kilohertz forms one. That's the granularity. You have each segment in the frequency domain 180 kilohertz long. Okay, now something called resource block in short RB, is defined with every 12 kilohertz in frequency and one slot in time. So there will be 12 times 7. If I count 12 subcarriers this way, and then this way I count 7. Once I take one slot, then I have 7 symbols. Then how many symbols I have for in this whole range? 12 times 7. Okay. So normally you have 84 symbols for transmission. But if you use 6, then there are 72. Now these are called resource elements. So each resource element actually transmits one symbol. These are the resource elements at the lowest level in the granularity for radio resources. Okay. So these are radio resources for wireless communication. But we are grouping into resource blocks. When you have some data transfer, then you are allocated in terms of resource blocks. Like you are doing, say, some downlink data transfer. You're downloading something. The network will tell you that you have, these resource blocks are carrying data for you. Okay, so you will be given, say, in a over this slot period. Okay, some of the resource blocks. We know that this way I can have, well, let's see how many resource blocks then I can have. Now we know that there are grouping of 12 subcarriers or 180 kilohertz. Yeah, so let's check how many sub resource blocks I can have at the maximum in the frequency X domain. Okay. Well, if you divide 300 by 12, you have 24, or 900 by 12, you have 75, right? So you have 5 resource blocks possible in one slot, right? As you go through the frequency range, okay, you have 12 subcarriers forming one block, and this way you can accommodate 75. So in one slot you have 75 resource blocks. However, if you take one subframe, so then you have 2 slots, then of course you have twice as many as shown here, 150, right? 150 resource blocks. Now in one slot, if you are given, say, out of 75 for your downlink data transfer, you may be given 5 resource blocks, and the network will definitely indicate. So you will be reading only those 5 resource blocks and capture your data. Okay, so that's how it works. Depending on your radio link quality or something else, you may be given higher number of resource blocks or lower. Somebody else may be prioritized, okay, and he may be given a larger share of the radio resources. Okay, and how is it done? He just given a higher number of resource blocks. So it's the number of resource blocks that define how much share you have currently. Okay. Okay. Well, now for SCFDMA, okay, few things I will I'll show the next day. Okay, like we are not mentioning today why we have 6 same resource elements. Okay, how to do that and what this cyclic prefix is. This kind of things, or the, I mean, as I said, that the how you fit in the whole size. I mean, what are the exact length of the symbols. These things I'll show the next day, inshallah. Well, WiMAX also started off with WaveDMA. Okay. Well, the basic technology for modulation is OFDM, orthogonal frequency division multiplexing. Okay. Or division multiplexing, yeah. But when you allow access, okay, when you use, say, TDMA, how do you call it? Time division, multiple access, right? What is the exact term? Is it?
Sir, I think it would be
multiple
multiplexing. Multiplexing.
No, multiplexing is one term. Or okay, let me quickly check on that. You can go online. Yeah, multiple access, right? So, I mean, the terms like multiplexing is when you use the term WaveDM, then you call it orthogonal frequency division multiplexing. Okay, and when you use this, I mean, when you just sort of indicate that you are using this to allow multiple users to access your resources, then it is called multiple access. Okay, I'm writing down the in the chat box. I'll write down. So that's the basic technology, and in fact, you can use it for a single user. You have the benefit of flat fading, even for a single user. Okay. That benefit you don't lose. Now, if you use it to allow multiple users to access the resources together, like you can do that because you have now different subcarriers. So you can allocate some subcarriers to somebody and another set of subcarriers to somebody else. So this way, multiple users you can allow to use different parts of your bandwidth. And that's how also in the time domain, you can actually allow, so WaveDM, okay, you can time domain, you can allow in one, say, subframe, you can allocate some users, but you may not allocate the resource blocks to a group of people. But in the next subframe, those guys may be assigned the resource blocks, and the first group of people may not be. Okay, so this way, in the time domain also, you can allow multiple users to use the resources. So this is called multiple access technique. And so the TDMA, FDMA, these terms have multiple access at the end. MA at the end for TDMA or FDMA indicate multiple access. So the same thing you can do here but with the help of OFDM. When you do that, then it is called OFDMA, okay, which means that you don't then mention multiplexing, you use the term multiple access. Okay. So we have already hinted how you allow multiple people to uh, okay. Now, WiMAX guys also used OFDMA and from the beginning, and they used it for both downlink and uplink. When it was the time for the inception of LTE, they made a small difference. In the downlink, they kept the WebDM technology, so it is WebDMA in downlink. But for uplink, they chose something a little different. Okay. It is close to WebDMA, but it has some difference. Well, this concept of WebDMA brings you the advantage of flat fading and also allocation of resources among multiple users are actually more convenient here. However, the problem is that in that case, in the case of WebDMA, the power level can vary too much. Different subcarriers may require different levels of power, and I mean, you need to have your power amplifier to work over a large range. Okay, like I mean, maybe normally you are working at a very low power level, but for some frequencies or for some cases, you also need very high power operation. So when you need that, you need to support all these things, and so you have a wide dynamic range of operation. Okay, large dynamic range. Okay, sorry. When the amplifier is designed with large power amplifiers are designed with large dynamic range of power levels, then the power efficiency of the amplifier is not great. Okay, so you have to have a linear region, for power amplifiers, that it starts saturating if you I mean the power level, it keeps increasing, but then the curve starts bending. But so if you have to have linear operation over the whole dynamic range, otherwise there will be distortion, right? So as you operate with a linear range of availability of power, linear range of power capability for the power amplifiers, then this amplifier doesn't have a very good efficiency. Okay, the output power and input power doesn't have a very good ratio. Well, in the downlink, it's not a problem because you have a bulk supply of power. You're connected to the mains or the bulk power supply. So if it is not efficient, you have more power investment. You actually consume more power That's not a problem, because for communication purpose, the total power level is never too high. It's never in terms of megawatt, right? It's always in the kilowatt range. So, well, the poor efficiency doesn't matter. But in the uplink, it does, because you use a mobile device, which you don't like to charge very often. You want that it has a very good power efficiency. Okay, so you don't have to charge it very frequently. So power efficiency does matter. Now, in the case of ODM, as I said, that it's a problem, but in the single carrier, you don't have that problem. When you work on a single frequency, okay, you modulate on a single frequency or single carrier operation that you have experienced in all the previous courses, then I mean, this problem is not there with the power amplifier. So what is done in the uplink is something in between single carrier operation and OFDM operation, and it is called SC-FDMA. There has been a few different variants now for SC-FDMA, but for all of them, the challenge is how well they can reduce the peak to average power ratio. Because I said that at some frequency you have large power requirement, okay, but the average power level may be low. Okay, and that if you can reduce the PAPR, peak to average power ratio, then the power amplifier can have better efficiency. Okay. So the different variants of SC-FDMA offer different quality of peak to average power ratio, PAPR. Okay, the lower it is, the better. I mean, you can have more efficient amplifier. So anyway, this solution, which is a combination of the two, single carrier and OFDMA, is has a much lower PAPR and better efficiency. So your battery doesn't drain out very fast. Okay, and battery of the phone. Now, in this case, you have still subcarriers. You still have subcarriers, but when you transmit, okay, it is the transmission from the phone end, UE end. All the subcarriers have to be contiguous. Okay, they all have to be contiguous next to each other. So, because there will be an overall, in this technology, there will be an overall single carrier effect. It is not completely single carrier, but sort of combination. Okay, and there is a single carrier effect created. So it is called single carrier FDMA, SC-FDMA solution. Okay, so it also has subcarriers, and it also has the same kind of splitting in the time domain and in the frequency domain. Like the subcarrier spacing is 15 kilohertz, and in the time domain you have slots, radio frames, one after another. So the same kind of divisions you have both in time domain and frequency domain in the uplink. Okay. Now this whole thing we can actually call time frequency resource grid, because it looks like a grid, right? I mean, just in x axis and y axis you draw lines and form a grid. So time frequency resource grid. Each element in the grid is called resource element carrying one symbol. So the same kind of time frequency resource grid you have in uplink, and also in the same way you have this kind of resource blocks. You have this kind of 12 resource blocks with 12 by 7 resource elements, or 72 resource elements. So all possibilities are there. Okay, so I mean the resource block definitions, the resource grid formations, all of them are exactly the same. Okay, so the number of resource blocks we have exactly the same in uplink. Okay, that's an introduction. Now we'll be discussing, but let me ask you if you have any questions or not.
No,
Or okay, then let us start discussing channels. Here, it will be again a short discussion. This let me tell you what presentations we have. Okay, now we'll discuss the different channels in LT. Thereafter, we'll discuss downlink synchronization for LT. We have done it for UMTS. Okay, so after this small presentation, we'll do it for LT. Actually, the next day we'll do that. Thereafter, we'll discuss uplink synchronization for LT. Okay, and these discussions will not be very long. But after that, we'll have a long discussion. That will be resource allocation, how you allocate different resources. Because there are few things associated, we'll have to address them too. And anyway, so okay. There are different channels defined both in downlink and in uplink. Okay. And these channels are defined at different levels. Like we have physical layer, we have MAC layers, we have RLC layers. Well, in the physical layers or in layer 1, you have these downlink channels. The whole terms for all of these channels, I will show you later. Okay. From time to time, I'll show you, but they are not important. You don't have to memorize the whole terms for the channels. And usually, we'll be using different acronyms. So the whole terms, I don't want you to remember. And even if you have to, if you had to remember, that would not. If the exam, if I asked you this kind of things in the exam, that would not be a problem for you any longer, because we'll have an open book exam anyway. So anyway, now this one, PDSCH. I'll tell you the whole terms, but you don't have to remember. Physical downlink shared channel. Physical downlink shared channel, PDSCH. So that carries the data. The actual data is carried on this channel. Well, but there are many different control operations. And this type of control activities are conceptually separated. Okay. Not only conceptually, how you manage them within your time frequency resource is also an issue. Okay. So for that purpose, you also need to know which part of the resource grid you should use for this particular control function. So based on the control functions, different channels are defined. Well, this purple one, you can forget. We can leave it out. This whole thing. Okay, starting from here, MCCH, MTCH, MCH. This whole thing is for MBBS, for mobile TV purpose. So that's no longer important, although I spent a lot of time on that before. Now, this one we will talk about later. It's also not very important. A part of the system information is carried here, but a very small part. But this guy, the red one, okay, is the most important thing for us. PDCCH, okay, which is called Physical Downlink Control Channel. PDCCH. Well, now you see that there are two other channels here. Now you can see that we have some other channel definitions at upper levels. Like from here, I mean, this is actually a connection from the MAC layer. Okay. And here you have at the RLC level. But these channels don't have any mapping from upper layers, meaning that the physical layer itself maintains the operation of these channels. Okay, I mean MAC has no control over them. MAC doesn't need to. Physical layer independently control the operations of these channels. But in the case of your data transfer, your MAC layer, actually from upper layers, you receive data from the application. Okay, the top layer in your 7-layer configuration protocol stack. You receive some data and then they are forwarded, and then MAC layer receives, and then MAC layer packages, okay, and forwards it to physical layer. Okay, so I mean here MAC packet is created and forwarded to this PDSCH, which transmits. Okay. This one also something we will discuss later. This paging channel, we'll discuss it later. For uplink operation, the uplink data is carried on this channel, physical uplink shared channel. Okay. People in the industries call it, in short, push. Push. Okay. And that is that also comes from the upper layers. Okay, I mean the application running on your phone. Okay, the software running on your phone will create some data for transmission, and it will forward to the lower layers. Okay, then on, and finally it will be. I mean the MAC layer will receive and create some MAC packet and forward it to this upper push, okay, the physical layer. The physical will transmit it on the push channel. There are only two other channels in the uplink for control purposes. This one is called physical uplink control channel, and in the industry people call it push and push. And we'll later discuss what it is for, and it is called PRACH, okay, physical random access channel. Okay. Now we will discuss a little bit about what happens when you first power up the phone. Okay. Well, the first thing is the frequency sweep. I mean, formally, I'll give a list of all these activities later. But to go further in our current presentation, I need to say a few things. I mean, it's the same for your 2G, 3G technologies too, that it will scan and find out. I actually mentioned it before too. It find out in which part of the bandwidth, part of the bands, okay, you have energy in the downlink. So if the phone supports say 4 different bands, it will check the downlink part of all these bands, the whole of the bands. For all 4, it will check the whole of the bands and check where there is some transmission, there is some energy or power level for signal is available. In that part, it tries to synchronize. It performs the synchronization operation that we have described for CDMA. It is downlink synchronization. Okay. With downlink synchronization, it can capture the symbols, okay, one after another, and also it can identify the cells. Okay. Once you do that, you need to be able to start reading. Okay, then you also select one of the cells. Okay, I'm just talking about the first powering up of your phone. When you have just powered up, you haven't made any call yet. You've just powered up. Okay. So it will then select just one cell from whatever it is receiving. It may be receiving significant power levels from 10 or 12 different cells, but it will select just one from them, and that will be the best in terms of the power level or the signal quality level. So signal power strength or signal quality. So these are the criteria for selection of the best cell. So it will select and it will consider that cell as its serving cell. So from then on, it doesn't hear other cells around. Okay. Well, for some purpose, sometimes it listens to what other cells it has around. But as the serving cell, it considers just one cell always. That the transmission from that cell, it starts reading. It has to read different types of information from this cell. Okay. Like the cell will always be transmitting some information, which I mentioned yesterday, some broadcast information. So it has to read those broadcast messages, the SIP messages. For this purpose, it needs to be able to identify how the data can be read or recovered. So let me show you how they work one after another. At the first level, after that synchronization operation, okay, the first step will be capturing this channel, PCFICH, physical control format indicator channel. The whole term you don't have to remember. Okay, to be honest with you, actually, I myself forgot the whole term for PCFICH, so I quickly switched to this slide and read it for you guys. Okay, now this PCFICH channel carries just one piece of information. Well, and I'll tell you what it is. And after reading this one, the next step for the EV is to read PDCCH. So there will be transmission in the downlink from the E node B for all these channels. First, it captures PCFICH and reads it. Once it reads it, then it can read PDCCH. Okay. Now we know the time frequency grid. In the time frequency grid, we have subframes one after another, and these subframes are the granularity for management of control. Okay. The control, I told you that the power correction commands can be sent in every millisecond. because it can be sent in every subframe. So subframe is the granularity of control level, control functions. Now in every subframe, there is the control region, and that ranges over the whole frequency bandwidth. Over the whole frequency, I mean all subcarriers it take up. If you have 1200 subcarriers that you have for 20 megahertz, then all these 20 megahertz, 1200 subcarriers will transmit this information for control. But in the time domain, it carries a small part. How much? It can be just one symbol, as shown here, just one symbol, or it can take up two symbols, or at the maximum, it can take up three. Okay. So it will always be there in the downlink, and it will be either three, it will be 3 or 2 or 1, one of these three. These are the three options. But if it is 2, then it will be 2 throughout the whole frequency range. If it is 3, it will be 3 for the whole frequency range. Okay. All the subcarriers will be using, this part, all these three symbols for control purposes. So it is called control region. Now this control region includes these three channels: PDCCH, PHICH, and PCFICH, which are not linked to upper layers. Okay, so the control region is occupied by these channels only. Here PDCCH is the most important thing. You need to read it for further activities. But before you read PDCCH, you need to know how wide your control region is, whether it is one symbol wide, or two symbols wide, or three symbols wide. Now the PCFICH has the only purpose that it tells how wide it is, how wide the control region is, 1, 2, or 3 symbols wide. So you see just one piece of information. PCFICH represents whether the control region is taking up 1, 2, or 3 symbols. Now PCFICH itself is transmitted on the first OFDM symbol on each subframe. And in the frequencies, it has a fixed location. I won't go into the detail, but it has some fixed location. When the UE synchronizes, okay, once we go through the synchronous procedure, it will be clear that the UE can find out the center of the transmission. So around the center, in the frequency, around the center, PCFICH sends some symbols at some fixed locations around the symbols. So those locations the UE first read, and then it can find out how wide it is. Okay, how wide the control region is. When this PCFICH symbols carry the information, okay, whether it is one, it has different code lengths, the bit sequences, different bit sequences for 1, 2, and 3 symbols. Yeah.
Sir, we have a class now from 11:45.
11:45. Oh, we are close to that.
Yes, sir. Sir, before ending our class, we would like to have a discussion on the quiz. Sir, about the quiz. Can we have it next Thursday? I mean, today is 15th, so next Thursday would be 22nd. Yes, sir. 22nd.
The class tests carry more weight, right? It's 10%.
Yes, sir. It's double mark, no, double the weight.
Yeah. So I was just planning that we might have one test before Q1 exam and two after. In total, we have to take 3, right? So we may
Sir,
take.
it would be 4. It would be 4, and out of them, best 3 would be taken.
Oh, I see. Okay. 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 Let's go ahead with the test on next Thursday. Okay. And let us decide the syllabus. We can CDMA we should include, and do you think we should include? So how should we go? Everything from CDMA, the whole of CDMA, whatever we have covered from CDMA, maybe the syllabus. How is that?
Sir, is that the slide number 2 and 3 we covered, and we started slide 4 in the previous class. So slide 2 and 3, sir.
Yeah, in terms of.
Yeah, in terms of what you told, the whole CDMA, it's slide 2 and 3.
2 and 3. 2 and 3. Sounds good?
Yeah.
What do you think?
Yes, sir. That is good.
And sir,
Okay.
quiz
Yeah.
sir, আগের মতো নেওয়া হবে স্যার ওই হোয়াটসঅ্যাপে সাবমিশন?
Google experience, sorry, I have a better experience with Google Classroom. Let us use that.
Already.
Okay. Yeah, I mean, we'll use Zoom for invigilation purpose, but the test we can take using Google Classroom. Okay.
So, as you said, it will be an open book exam.
Yeah, it will be. Yeah, definitely it will be. And it will, if you have something to write down, capture image and then submit, then I can use the assignment option there for Google Classroom.
Yes, sir. There is an option to give a form, and if we need to upload anything, we can upload in the form or something like that.
Right. So we'll do that, inshallah. So next Thursday, so can we use, do you think we should use a part of our class, or you want it at some other time?
Sir, if it is convenient for you, then we can use our class time if it is convenient.
Right. I mean, for me, it's okay whether you do it here or.
Sir, as we did in the last semester, that we kept like 20 or 25 minutes for the quiz, and rest of the time we had our class. That can be done.
Okay, let's go that way.
Sir, if it is possible, you can also fix the quiz after Asr or Maghrib if it is convenient for you, sir. In that case, we will have times for preparation, and you will also have more time for the class, sir.
Nothing is inconvenient for me, but nothing is inconvenient for me.
Sir, we can discuss,
I think we can
fix, sir, after discussing with you again, sir, and after discussing with all of the students, sir.
Okay. But we can use our whole class period if we take it at some other time slot.
Yes, sir.
Okay. Yeah. So maybe you just suggest me some time slot. It should be around 20 minutes. Okay. We'll meet
sir.
then and take the quiz. Okay.
Okay.
So
sir.
any time you can suggest me any time in the next week. Okay. You can just send me a message. I'll prepare accordingly.
Okay, sir. Thank you, sir.
Okay. I'm sorry. I didn't notice the time. Okay. I mean, we could have stopped earlier and asked for questions. But if you have questions, we'll answer them in the next class, inshallah.
Assalamu alaikum.
Salam.